All right. All right. Our next speaker is Katya Scheinberg from Lehigh University. She's going to talk about minimizing training error and area under the curve.
Okay, thanks a lot for inviting me. So I was told that I'm supposed to bridge discrete optimization and continuous optimization, right, for this workshop. And I'm not really working on discrete optimization, but this is why the training error and AUC, they are really discrete problems. And it's just, this is kind of a case study. What can we do? I'm not necessarily advocating that that's what we should be doing with these problems, but it sort of was interesting to me, at least. I don't know. I'm hoping other people will find it interesting. So the training error in AUC, I'll talk about what it is. I mean, obviously, everybody knows training error, but AUC, not maybe everybody knows. But it's a standard in the industry to measure your classifier. Many people treat it as some kind of a voodoo thing that needs to be good, right? Needs to be close to 1. So we will, but it's actually a very simple, has very simple mathematical expression and can be therefore optimized. Okay, so I'll talk about these two functions. They're both step functions, where they come from. So the basic setting of machine learning, most of you, of course, know it, but just to define notation. So we have a sample set of training data, or whatever, available data. And we are going to, so it is distributed according, it has some distribution, which we don't know. And it's pulled out, the data is pulled out as IAD from this distribution. And then the goal is to find a predictor which is good for this distribution, right? So ultimately what we want to do is we want to find a predictor. And usually we need to narrow down our class of predictors to some particular class parameterized by W, right? So this W in linear predictors is your just linear W, that defines the hyperplane. In neural networks, it's all the weights on all the neurons. But essentially, this is the function that you're trying to somehow measure its quality in terms of predicting your output Y. And then you want to maximize the probability of a good prediction. And this is deliberately left vague. OK, but in case of, so I'm going to talk about binary classification exclusively. So in terms of in case of binary classification, it's a very specific thing that you want to optimize. You want to optimize the probability that your label and your predictor have the same sign, right? So binary classification is plus minus 1. The labels are plus minus 1. So you want to basically predict the correct sign of the label. And you measure your accuracy as the expected probability that you have a correct prediction, right? This is what you want to ultimately optimize. And then, of course, since you have a finite set and you don't know your distribution, you don't know how to optimize this directly. So what you do is you look at this function, right? And this function is just simple sample average approximation of that true optimization problem, except for here I've switched to a minimum just because it's kind of more familiar. So instead of maximizing the correct prediction, I'm trying to minimize the number of wrong predictions, right? This is the same thing. And this is 0-1 loss, which is basically measured as 1 whenever my prediction is wrong. OK? No questions so far, I hope. So this is when I first started hearing about machine learning problems. Everybody says, well, this is great, but this is an NP-hard problem because this is basically a stepwise function. But really, this is not even the function that we want to optimize. We want to optimize this function. It's not clear that what does it mean NP-hard anyway? Who wants a solution of, well, yes, I mean, right, yes. No, but Ben has this other definition of F-hard problems. This is not. This problem. It's NP-hard if you want to optimize this. Exactly, but who really wants to optimize this exactly? We want to optimize this function, right? So this is what I'm kind of will be talking about a little bit. Just to, again, everybody knows this, but typically when people, like in machine learning course, they say, well, this is a hard problem to optimize because it's non-convex and whatever. We're going to replace this loss with the logistic loss. And logistic loss has nice properties, and it does. I mean, there's no question about it. So it's nice and convex if predictor is linear and so on. So this is what typically is optimized. But let's go back and look at this function. So I'm now going back to optimize accuracy because it's just a little bit easier for me to use notation. So this is my function, right? My function is the basically indicator function that my output has the same sign as the label. And then I average them out. And this is accuracy for a given data set for a particular W. OK? So my function would look like this. What's the problem with this function? OK, I don't know if exactly if it'll look like this. But it'll probably look something like this. This function has a fairly clearly defined minimum. And the problem is that we can't compute the derivatives. Rather, we can, but they're going to be 0 everywhere. Right? So this is the biggest problem with this function. It's not going to be hard. It doesn't really matter. What matters is that derivatives gives us 0 information. So it's an interesting case. Like I've been working on black box optimization, right? Derivative-free optimization. Usually you just say, oh, I don't have derivatives. Here you have derivatives. They're just completely useless. So can we do something about this? So clearly we are hoping that the function that we actually want to optimize looks something like this. It may not be convex, but it's probably nice. And it probably has some kind of a decent minimum. This is the function and expectation, right? So this is what we actually want to optimize. Not this, but this, right? So we just don't know. So this is a surrogate for this function. So let's first think why do we think the function is smooth? Well, I don't know. It's smooth. Sometimes it's not smooth. Some other times for sure, this function. But it depends on the distribution. But typically, the only distribution we can think of is normal distribution. And for normal distribution, it turns out to be really smooth. And maybe this has been done before. We haven't found it with my student in the literature. It's sort of a fairly simple analysis that if you take basically 2 normal distributions and you're trying to separate them by a linear, so I'm fixing my classifier class to the just linear predictors. So if I want to separate them by a linear classifier, I can actually write the expected accuracy as a function of the moments of the of W and the moments of my distribution. So let's see. I have one normal distribution with first and second order moment mu p and sigma p. Here's mu n and sigma n. These are negative and positive class. And then the expected accuracy, which is this function of W, can be just written like this, where this is just the typical probability density function for normals. And the arguments here are essentially just the combinations of the moments for the original distribution and W. So this is a smooth function of W. That's the bottom line. Okay, it's a very nice smooth function of W. Moreover, you can actually compute the gradients of this function. There's nothing black box about it. Okay, so it was kind of interesting. We thought, okay, well, no, clearly we don't. First of all, we don't know the distribution is normal, and even if it is, we don't know the moments. But let's just try it and see how it works. So we've tried it. What did we do? Let me just go back. We take data set, right? We compute. So if you know the moments, if you know it's for sure, we just plug it in and take this function and optimize it with using gradient information. But if you don't know the moments, we just estimate them from the distribution, right? From the sample set. This is approximate. So here we tried it on artificial data. Number of samples is 1,000. Produced 2 kind of nicely, relatively separable distributions. Then exact moments, because it's artificial data, we know the moments. These are approximate moments, and this is what you do if you run logistic regression on the same problem, and what you get. So what are we having here? It's basically the, so these are different dimensions, and basically this is the final accuracy that you obtain from your linear separator from each of these optimization runs. Okay, so this is the direct optimization. This is the best you can do. Logistic regression doesn't do quite as well, which is, should be the case in principle. And this is the approximate moment case, which does actually quite well when the dimension is relatively small. And when dimension gets larger, it starts not doing so well here. And that's reasonable because my number of samples is fixed. So if I have more samples, I can improve the quality of my estimates of the gradients. So here I'm computing gradients that are inexact and not in a very clear way. So it's not like a stochastic gradient. It's some, well, yeah, I'm not sure it's a stochastic gradient. I actually haven't analyzed it. But because I'm computing these moments in some approximate way, and then I'm plugging into the gradient, I don't think it's going to be exactly unbiased estimator. It's a stochastic gradient, but it's not necessarily unbiased. OK, so the interesting thing about this is like something that there is no really, once I estimated the gradients, once I estimate the moments, I have direct formula for the gradients. There's nothing dependent on n here. The only thing that depends on n, the number of samples, is outside the optimization process. So it's actually very cheap. I mean, if dimension is not very big, this is a very cheap algorithm. And it runs faster than logistic regression, because logistic regression needs to compute the access data every time, right? So does it make any sense? Does it work in real life? OK, real life is a strong word here on small subsets of AUC, UCI data sets. So that's definitely not real life. So we tried it. We thought it's not going to work at all, because, I mean, this is under assumption that distribution is normal. But it actually surprisingly works well. And especially look at this case. We got much better accuracy than, for example, something can be obtained in logistic regression in this amount of time versus this amount of time. So it works sometimes. It doesn't work some other times. Here, what happens, we're still going to explore what's going on. But essentially, the way my student implemented this right now is she's just doing line search with the gradient step. And of course, gradients are basically, it's a guess whether the gradient is right or wrong. And right now, if the gradient is wrong and it happens to point uphill, you just get stuck. You don't move anywhere. So some kind of maybe additional stochasticity may help here, but this is where the cases where things get stuck, so we don't get good result. But who knows? So it's I don't know. I found it fascinating. It actually can possibly work. And yeah, it's so. We'll see where it goes. But I'm not necessarily advocating these methods. It's just, it sounds kind of as an interesting possibility. And then, OK, let's talk about AUC, which is very similar, really. But AUC that's where we started, because it's somehow, unlike accuracy, it is considered even more sort of black box weird function. But essentially, it's the same thing. So what is AUC? Accuracy is not always a good measure. So let's think of basically imbalanced data sets where you have, so you're trying to predict spam versus non-spam email, right? So you have 99% of spam email and 1% of non-spam email. So if you label everything as spam, you have 99% accuracy. So you're great, right? But except for it's obviously an awful classifier, because all your email goes to spam. So the measure of the classifier for imbalanced data sets is not usually your accuracy, but it's the trade-off between false positive rates and false negative rates, or true positive rates. So what people sometimes do is to find such a classifier that has good AUC, they just weigh differently the positive and negative class, right? So if your spam is only 1%, you just put a lot of weight on incorrect classification of your non-spam emails, and you hope for the best. But it's not necessarily the best way, again, to deal with things, because then you need to pick up these weights, and then the output depends on weights, and so you're biasing yourself to a specific selection of weights, and so you have to then choose the weights that give you the best AUC, and people sometimes do that. So what is AUC? Is like in industry, is defined as an area under the ROC curve, right? The trade-off between the positive, false positive, and true positive rate. So this is different. I'm not going to explain what it is. If you don't know, it doesn't really matter, because on the next slide I'll explain. I'll show much better a much more clear definition how you compute AUC, but the essential thing is it's the area under a curve, and the curve, if the curve looks more like the blue one, then the area is bigger and it's closer to 1. So AUC is something that is between 0 and 1, and you want it to be as close to 1 as possible, right? But the simple way to compute it is the following. So you take positive and negative class, let's say they're distributed according to some distributions, right? You pull out your data from those from positive and negative, and then instead of computing the error of your predictor in the sense that label times this predictor bigger than 0, you just count the number of positive examples that are basically being labeled higher than the negative examples. So you look at all the pairs, and for each pair you see if you have a correct ranking, right? So this is also known as the ranking loss. So it's very, very similar to the accuracy, except for now you're just computing this error for all pairs. And the kind of important thing to note that computing this function value, you think should be quadratic in terms of, like, let's say you have, well, in imbalanced data sets it's a bit different, but let's say you have n over 2, so n data total and roughly n over 2 in each of the data sets, then the amount of work here is scaling is n squared. But except for it's not, because you can actually do this by first, by computing all of this for all the data, and then ordering the data, and then it's n log n actually, if you use quicksort. So it's good. You can do that with this loss, but if you replace this 1 here with a logistic loss, you can no longer do that. So if you replace this with a logistic regression kind of approximation, every function evaluation becomes quadratic in n. So but on the other hand, if you replace it with hinge loss, it is again n log n. So one has to be a little bit careful with this. How do you treat this AUC? Even though it also looks like a 0-1 loss function, okay? All right, so back to the same thing. We don't want to optimize this. We want to optimize the expected loss, and expected loss or expected AUC, which is essentially the probability that when you pull out 2 points, one positive, one negative, what is the probability that your predictor is going to rank the positive one higher than the negative, okay? And again, so is this a smooth function? I'm really curious because even probably from geometrical perspective, one can analyze this for various sort of assumptions on distributions. But again, we just did it for normal distribution or jointly normal in this case because it's positive and negative class. That here you kind of need to, you don't need to, but you can work with the jointly normal distribution, and then you again have exact formulation for this probability function. And it again is just some probability density function from the normal with a particular form of the moments which are derived from the moments of your distribution of your data. Okay? And again, we can do the same thing in terms of we produce random data sets that are artificial coming from normal. And we compare it, this time not with logistic regression, but with hinge. And then we can see how well we're doing. And, of course, here we do better than here. But CDF, so with the approximate moments, we don't do quite as well, but we still do reasonably well. I mean, this is artificial data, just validating that we do things correctly. And then we did this on the real data sets as well. And again, it surprisingly kind of works. It's not always working great. Here we didn't get, we got kind of stuck. But on real data sets, we managed to get some optimization. And again, the left column is a lot cheaper to compute because it's completely independent on the number of data. Well, you compute the moments, and then you run your optimization. Whereas here, you have to do this n log n steps every time if you want to access the entire data. Okay.
Katya, can you go back a second?
Yeah.
So you're calling out the ones where you're doing poorly. Okay, I'll just check. So those are the ones. Those are the worst ones.
Right. Yeah. Right. The rest are pretty much.
That's
yes.
unusual. Usually people highlight the best ones.
So I probably would have done it if I had really something that it really beats. This is the annoying thing. So far, the only thing I can show is that we do it faster and we can do as well. Right? That's the only thing, right? We're somehow not managing to get better result, but maybe it's not surprising, after all. And these are UCI data sets that are overfit by so many algorithms, right? So it's kind of hard to get an improvement on them. Anyway, okay. So now next, like, okay, this works sometimes, it doesn't work sometimes. Great. Maybe we can improve it. Maybe we cannot. What should we do in general? Should we use the gradient estimates? Yeah, maybe. But on the other hand, these gradient estimates that I was suggesting assume that distribution is normal. But the function estimates that I can compute from just the computing AUC, they're true estimates. They're unbiased estimates of the true expected value function that I'm trying to optimize. So I can actually optimize these functions directly just using function values. I can't use maybe the gradients if the gradients are incorrect, but the function values are useful for me. So here I can indeed use something that does not use derivatives. And this is what we did, and I'll show you some computational examples, and then I'll go into theory. Why are we thinking that this is reasonable? And the reason we say it's reasonable is because we can basically assuming that the underlying function is smooth. And I showed you that the underlying function is something particular in the normal distribution, but the smoothness is a much broader class. So much broader class of data will give us smooth expected value functions. And if they're assuming that this is smooth, and we can estimate the function to some accuracy, we can run methods that converge. And this is what I'll talk about in this kind of the end of the talk. So the current problem with using these methods, I'm just saying up front, is that the derivative-free methods don't scale as well as the gradient-based methods with W. And that's very possibly going to change because there hasn't been actually worked in trying to scale up these methods until recently, but I think Jorge is going to talk about this. And there's a lot of interest in scaling up these methods. And this is one example, for example, why we maybe should, why they may work well. But another alternative, this is just, so if we can scale, so here, we're saying that we cannot scale with the dimension W. So maybe another alternative is just to reduce the amount of variables that you are optimizing over. And that's actually well known as hyperparameter tuning. I'm not going to go into details of that, but hyperparameter tuning essentially does this. It just selects few parameters, then runs some kind of a method that computes the eventual W, for example, logistic regression that depends on some parameters, and then computes AUC on top of from this W that is being computed by some other method, and then goes and optimizes the resulting function, the AUC function, right? My point here is that the hyperparameter tuning has been used recently quite a lot, and there's a lot of papers on that. But again, under some conditions, the underlying function will be smooth, and then you can actually have some guarantees about the method's convergence and convergence rates and things like that for that case, even though AUC looks like a very strange and black box function. Okay? All right, so just a few, I have maybe some too much of computational results here, but what I'm just trying to show, this is basically the bottom line. So we tried the trust region derivative-free method, which I'll talk about in a minute. And we'll try it on various, again, data sets here, the same thing, and basically compare it to the standard AUC. And again, the optimization of AUC in a standard kind of hinge approximation. And again, we get about the same answer. So we don't really get something much better usually, or better at all, as a matter of fact, unfortunately. But we usually get it faster with fewer function evaluations, because you kind of directly optimize the true function that you're trying to optimize. Okay. Here is a larger data set. And then here's a comparison. Actually, it's a natural thing. What we did with the larger data set is that we tried to optimize it with the this assumption that it's normal and using the gradients, right? So we got somewhere, which was not so great. This is the kind of the best AUC we're trying to get. This is what we get with just running derivative free. So it's clearly better, because the gradients are really not correct, so they're not telling you the truth. But the function values are much more correct. So we get, and this is just warm starting. So you can use the initial incorrect gradients to run your method for a while, and warm start the derivative free method. So we did that, and it works reasonably well. Here, for example, it made an improvement with the warm starting. Okay, right. What else did I want to say? We compared our method to Bayesian optimization, because Bayesian optimization is very big for derivative-free optimization in the machine learning community. And again, results are similar, but the methods that we're talking about are much, much faster than Bayesian optimization, because Bayesian optimization is a global method and it really works very slowly. We compare it to the random search that Ben likes. And of course, random search really starts doing very poorly when the dimension grows a little bit bigger. And here we're hoping to kind of grow the dimension to some reasonable size. So we get better results than random search for sure. This is hyperparameter tuning for some particular case against Bayesian optimization. The blue line is ours. So we do well. We do fine. OK, so So now, why are we justified in doing what we do? Everybody can throw in some random methods, right, and show plots and say that we're doing well. But this is basically kind of why we started even doing this. So let's say we have the following situation. So now we have a function which is stochastic. We can't compute the exact function, right? And we may or may not compute the gradients. So this may or may not be available. This is always available, some estimates of the function. And we may or may not have estimates of the Hessian. Again, in this case, it depends how we compute them, right? So we assume, so the typical methods that are being used today assume this. They assume that whatever you have the stochastic estimate of the gradient function value and the Hessian, they're unbiased. We don't assume that. But they need to be sufficiently accurate somehow. And I'll explain in what sense. Okay? And I think this applies here, because in these complicated functions that are based on what I was just showing you, they don't necessarily give you an unbiased estimate of the gradient, but they probably give you something reasonably accurate. Okay? All right. So what we used is a trust region method. This is a deterministic trust region. I'll explain how it extends to stochastic. And not line search for, sorry, not line search, for a simple reason. Two reasons. One is we want to use second order information, and we're targeting non-convex problems, right? So we will be using second order information, whether we are building it from the gradients or from something else, usually from functions, but we can put in a Hessian estimate here, and it does not have to be positive definite. And if it's not positive definite, you cannot use Newton method directly. You have to use something like a, you can use cubic regularization. We're using specifically a trust region method. And there's also a reason that, at least in our analysis currently, it's essential that we're using trust region method, because the trust region step size does not allow you to do crazy things. You update the trust region in a conservative way, slowly, and it really kind of makes sure that everything works. So it stabilizes the method, okay? So what is a trust region method? So you have some kind of a quadratic estimate of your function, right? So we were talking, there was a discussion yesterday that Newton method is nothing else but second order Taylor series expansion. So exactly that's how we think of these functions. They're sort of like Taylor series expansions, except for they're not necessarily. They may come from something else. But there is some quadratic estimate, which hopefully is like Taylor series expansion. You minimize this model in the trust region. So this is 2 norm here, right? So again, the first talk yesterday was about using infinity norm. That's a very interesting application here. But if you have a non-convex problem, it's usually hard to solve the subproblem. So you solve the subproblem with a 2 norm specifically. And then we compute the improvement in the function. And improvement in the function is like line search. It's telling you basically whether you should accept the step or not. This is a typical thing, right? So for those of you who are not very familiar with trust region methods, here's the kind of a picture. Gray is my true function, and the blue is sort of this Taylor-like model. And here, indeed, it behaves kind of nicely. I can minimize it and find the minimizer of this model and check if the function improved at this new point. And if it did, I'll move there, and I'll make a step, and I'll construct a new trust region and a new model. And I'll continue doing this. But this is something that will never happen with the Newton method, because this is completely wrong model, right? This is not a Taylor model. And the whole point is that we may have something like this. It's because we're not requiring necessarily models to be Taylor model. But if it doesn't happen very often, then it's OK. So this is where the kind of the random estimates come in. Once in a while, they can be really bad. OK, so for deterministic case, the theory basically is roughly like this for the trust region method. So if this is my model, and this is, so we call them fully linear models or fully quadratic models to distinguish that they're kind of like Taylor, but not quite. So what does it mean, Taylor model, up to first order? It means that if my displacement is of the order of delta from the current center of where I'm expanding my model, right? This is my displacement. Then the function value changes as the size of this displacement squared, right? This is typical Taylor model requirement for the first order approximation. And then this is basically the same for the gradient. Now in Taylor model, again, the gradient will be exact, but from this, you basically get to this. Now, this is essentially the behavior that you need from Taylor-like model. Well, rather, yeah, this is fine. And the Hessian just needs to be finite. This is nothing but saying that the Hessian estimation is finite, is bounded. There's no accuracy here. It's just some constant, anything. And this constant can be anything, just fixed. OK? So if you get this, then you have a first-order convergence of a trust region method and the convergence rate to the place where your gradient is below epsilon is 1 over epsilon squared, which is the standard convergence rate of stochastic of gradient descent or any other first-order method. If you have a second-order approximation, then the rate of convergence to a second-order stationary point, so that's the local minimum, right, that we kind of maybe care about more, is going to be basically, so to reach the place where the second-order stationarity is below epsilon, it's going to be 1 over epsilon cubed. Again, this is standard. OK? So basically, what happens now? We have a stochastic method, which works like this. So it's the same thing. It's the same trust region method. Here, the model is assumed to be random. OK, so all these quantities can be random. You, again, go and minimize this model with respect to the trust region. And I just want to point out that this is important, that if, for example, I don't want to minimize my model exactly, there are recently methods in for trust region subproblem that are randomized and give you some kind of approximate solution to this subproblem with some probability, you can actually view it as having a random model and optimizing it exactly, right? You can kind of reverse engineer. So this hides here, the randomness here actually hides a lot of stuff of like using randomized linear algebra to solve your subproblems, which is something that would be very useful to maybe implement in derivative-free setting, for example, where things are need to scale better, or not just in derivative-free setting. Okay. So you have a random model, and then you also don't have the function estimates that are exact. So you have some kind of approximate function estimates, but you still do this. And this is a guess, basically. This tells me I am guessing if my function had improved. I don't really know because this is not a true function. It's an approximate function. But if this function is accurate enough with high probability, I'll be fine. And then there's an additional condition that basically requires the trust region and the estimated gradient to be of the same side. And this is essential for convergence, but it's not really, I mean, it's a technical detail in some sense, but it's really essential for, otherwise the methods don't work. Okay, so we have convergence results and convergence rates. And I just want to emphasize what does mean convergence rates, because these days with stochastic methods, the convergence rates are very different depending on what kind of methods are used and what they really mean, because it's convergence rates and expectation. What does it really mean? So in our case, it means a very specific thing. So to get to the place where gradient is epsilon takes random amount of time, obviously. We don't know when we get there. And it's a stopping time of a stochastic process, because your algorithm, when everything is stochastic, is a stochastic process. But at some point, something happens, and it's a stopping time. And then you can analyze the stopping time. And this is what we bound, the expected stopping time. This is very different from, say, the convergence rates of stochastic gradient descent. If those who know what it is, they are different. But the essential point is that we can get the convergence rates that are very similar to deterministic methods. Okay, and so these are basically the results. And the results are very, very similar to the deterministic case. So if you have, again, the first order method, the first order models. So again, we have to satisfy these properties, but now only with some probability. Okay, so this is basically what will kind of happen if I estimate my function values from samples, right? And I don't get always good estimates, but I expect to get good estimates with some probability. Then I have the convergence rate. Sorry, there should be 1 over epsilon squared, because it's the same as before. And if I have a second order method, so I have sufficiently accurate Hessian estimates. This is kind of second order Taylor model. But there's also an additional assumption, which unfortunately had to be introduced, which again is kind of like second order Taylor approximation. Then again, if this happens with high probability, then we have second order convergence, convergence to a second order stationary point with this rate. Okay? Right, so this is basically just tells you that we have a generic conditions on your Hessian, gradient, function value, everything. What does this really mean if we want to do just estimate things by sampling? So Jorge will talk about that as well, I think a lot more, but essentially just tells you how much you need to sample in every iteration. And it really depends on the size of your gradient, of your trust region. So you're currently at some iteration, you have a size of the trust region, you know how far you're gonna go, and you're going to basically know how big your sample size has to be in order to achieve appropriate accuracy with sufficient probability. So this is for first order convergence, and this is for second order convergence. So your function values have to be accurate, much more accurate than you say your Hessian estimates, because that's that's what the theory tells us. And these look horrendous because, of course, the trust region to the 6, 1 over that. So if trust region is 0.1, this is 1 over a million. So it looks like really a lot. Well, with a cloud, maybe we can afford it. But it's true in some sense. And also with deep learning, actually, this is not something I was talking about here, but with deep learning, it may be actually completely affordable to compute the function value much more accurately. But the Hessian computations with all the Hessian-free methods, for example, you need 30, 40, whatever conjugate gradient steps. You may actually save a lot by having a cheaper estimates of the Hessians. But that's kind of a side thing. However, the point is that we've tried, for example, optimizing AUC with just sampling data in a dynamic way, but not at the rate of 1 over delta to the fourth, or not 1 over even delta squared, but actually at the rate of 1 over delta simply. So just slowly increasing the step size. So it's not what theory tells us, but we still, not step size, sorry, the sample size according to the size of the trust region. And here you can see that this is basically, so this is the stochastic. Which one is stochastic? Stochastics are here. These are deterministic. So for example, this is the deterministic case. This is stochastic case. It does not get quite to the same accuracy because I think we didn't get quite sufficient number of samples in the end. But it does pretty well in 25 passes through the data instead of 110. Here in 40 instead of 250. So basically, it does kind of work. And then, to make it practical is a whole other, basically, thing. So what are the conclusions? I don't really know in that sense. We are just exploring these ideas. So maybe we should focus more on trying to approximate the gradients of these functions. It might be interesting. Or maybe we should instead focus more on scaling derivative-free methods. They'll be useful in other cases anyway. And then, analyzing the cases when these sort of step functions actually are smooth in expectation, and then we can guarantee convergence and convergence rates. Okay, thank you.
So when you were showing this example of like the synthetic example that you were feeding the model the normal distribution and it was working fine up to some point that the dimension like went too high. Mm-hmm. So I was wondering if by applying the simple dimensionality reduction on UCI data you could get better performance then, because it seems like the main bottlenecks at least on your synthetic data seem to be the poor estimates of.
Well, it's just because we only generated 1,000 samples for 200-dimensional problem. So yeah, I mean, I don't know. It's
that's what I'm saying. So I'm saying maybe if on UCI data you could, for example, do dimensionality reduction first, then you could even see
okay, right. So this is a whole other, this is the whole question that I don't know a good answer to. I mean, somehow. Can we apply dimensionality reduction to UCI data sets to actually get better performance of the algorithm where we use probability density functions, but with estimated moments? So very possibly. Or can we somehow, what can be done with the data to make it look more like normal, right? Yeah, exactly. I mean, very possible. I have no idea. Any suggestions would be great.
Was there an instance in which there was a data set that looked very far from normal, but the performance empirically showed very good performance as compared to?
I don't know. We haven't looked into it yet. Sorry. Like this was literally. I realized that I need to connect with discrete optimization, and we're like, let's do this. Let's try to run it, and we ran it. So yes. I mean, it's all open so far. So far, we have been optimizing these functions with derivative-free stuff, but I just wanted to see what happens if we actually use the gradients. And to our surprise, it worked in many cases. So yeah, I mean, it's all a question. Yeah.
So you mentioned one kind of warm start scheme. I imagine you tried all varieties of warm start schemes.
Yeah. So I don't think we tried all varieties,
well, I mean,
but
you tried your thing and then logistic as opposed to the initial
right.
stuff as a warm start to logistic.
So we haven't tried it for logistic regression because I don't know if there's. I mean, maybe there's a point. Maybe there's a point. I don't know. It's just logistic regression is solving a different problem. But yeah, I mean, maybe I'm just not sure why it would necessarily help. But but maybe it would, because then you'll still have dependence on n in eventual iterations, right, in logistic regression. And if you use stochastic gradient, then warm starting, it may not help so much. But yeah, with derivative-free, we definitely did this. And derivative-free has similar problems in some sense, that it also tapers off in terms of improvement. So this whole warm starting is not like a perfect idea yet. At least it's not clear how much it helps. But if it's non-convex problem, it should lead you to some maybe better local basin. But yeah, I don't know.